So far, we've been talking about one-dimensional functions and their Fourier transforms. We've learned that to take a Fourier transform means to decompose a complicated function into a series of simple sine waves. The idea is that if you were to add those sine waves back up together, adding them together, you would recover the complicated function that you began with. But in microscopy, we don't deal with one-dimensional functions. Rather, we record two-dimensional images. So the next subject is a two-dimensional Fourier transform. So to introduce one-dimensional Fourier transforms, I showed you how you could take a series of one-dimensional sine waves and add them up to get a complex function. To introduce two-dimensional Fourier transforms, I'd like to start with the same thing. I'd like to add some two-dimensional sine waves together to start to form a more complicated picture. In a one-dimensional sine wave, we have a variable, and the value of the function rises and falls in an oscillatory pattern as a function of that variable. In a two-dimensional sine wave, we have two variables that define a plane, and the value of the function either rises or falls depending on the position within that plane. So for instance, a two-dimensional sine wave I can represent with this piece of paper. If each position in space here on this plane is a position defined by an x and a y variable, the value of the function I could then represent as the height of the piece of paper. And so one two-dimensional sine wave looks like this, in that it rises. If this dimension is x and this dimension is y, this two-dimensional sine wave rises at low x, and then as x increases it goes through 0, and then it has a minimum here, and then it comes back to 0. So that's a two-dimensional sine wave that varies with x. A two-dimensional sine wave that varies with y would look instead like this, because it would rise at low y, go back to 0, have a minimum, and then come at higher values of y back to 0. So this is a two-dimensional sine wave. Now, to look at more complicated two-dimensional sine waves, I've written just a simple program that I can use to create a space and then add sine waves to it. So to create a space, here my dialog box says new image dimension. I'm going to pick a dimension of, let's say, 800 pixels. And it gives me a space, a plane of 800 pixels in x and 800 pixels high in y. And what I'll do is add a sine wave to that plane. Now, two-dimensional sine waves are characterized by two parameters, h and k. These are called Miller indices, and we'll talk more about them later. But they represent how many oscillations along x this wave has, that's the value h, and how many oscillations there are in y, that's the index k. So for instance, a h equals 1 and k equals 0 wave with an amplitude of 1 and a phase of 0 looks like this. So what's happening here is the value of the function starts at 0 here along this left side of the box, and then the value of the function rises, which is represented by brighter pixels here, and as it's a quarter of the way across the box you have a crest, a rise here, and then as we move to higher x values it falls back to 0, and then you have the minimum. At 3/4 of the way across the box in x, you have a minimum represented by the darkest pixels, and then it rises again back up to 0. This is the 1, 0 wave. In the piece of paper, this was the first wave that I showed like this. Okay, now let's look at a different wave. I'll create another box, again, of dimension 800, and let's add a sine wave. Instead of the 1, 0 sine wave, this time let's add the 0, 1. So now it should oscillate no times along x and one oscillation along y. And again, let's give it an amplitude of 1 and a phase of 0. Now this is the wave that we get. Now, in the way I've created the program, down here is the 0, 0 coordinate, and y increases as you go up the box in this way. And so because of that, here along the x-axis, or the function starts at a value of 0. And then as we move into positive values of y, at a quarter of the way across the box, we reach a maximum of 1. So that's the first crest. And then the function falls to 0, and then it approaches its first minimum, here 3/4 of the way across the box, and then it recovers back to 0 as it goes across. So that's the 0, 1 wave. Now let's look at another wave. This time, let's add a 1, 1 wave. Now this should have one oscillation across the box in x and another oscillation across the box in y. And we'll again give it an amplitude of 1 and phase of 0. Now you can see this is a diagonal sine wave. It starts at 0, 0. It starts at the function, the value of the function is also 0. But as you increase in x, it rises to a maximum a quarter of the way across the box, then back to 0, and then it goes to a minimum 3/4 of the way across, and then back up to 0, just like the 1, 0 wave did. But this one, as soon as you move off the x-axis, it behaves differently. Now in y, at y equals 0, it starts at 0 and rises to a maximum a quarter of the way across, and then a minimum here 3/4 of the way across the box, and then back up to 0. And so along this y-axis, it behaves just like the 0, 1 wave. But anywhere where the value of x and y are both non-zero, then you have a combination of position and a diagonal wave going across the box at 45 degrees. Now let's look at the role of phase. Now let's look at the 1, 1 wave with an amplitude of 1, but instead of a phase of 0, this time let's give it a phase of 180 degrees. Now what's happened is we've shifted the whole wave forward by a half of a wavelength. So here we start at 0 again, but instead of heading towards a maximum, we're now already halfway through the wave, and so we are heading down towards the minimum. And then we rise to the maximum, and then go down to another minimum and cross the box. So you see the phase takes the exact same shape of the wave, but it shifts it left or right, or forward or backward. And a 180 degree phase shift is half of a wavelength, and so it shifts it halfway. A 90 degrees phase shift would just be a quarter of the way. 270 degrees would be 3/4 of the way. And so that's the role of phase. Now let's look at combinations of waves. If we give ourselves a surface, and let's add a 1, 0 wave with an amplitude of 1, and this time let's use a phase of 90 degrees. Okay, so you're familiar with the shape. It oscillates only in x, and now because we gave it a 90 degrees phase shift, it starts already a quarter of a wavelength. So it starts at this maximum, and then it falls to 0, goes to its minimum, and then rises back to the maximum at the other side of the box. Now that we have one wave in our picture, let's add another wave to our picture. This time, let's add a little bit of 0, 1 with an amplitude of 1, and to make it simple, let's use a phase of 0. Now we've added two waves to our image, and the system is more complicated because now as we move forward through the y-coordinates, the 0, 1 wave starts at 0, it rises to a maximum, and you can see now we have a maximum here progressing down towards a minimum and then rising back to a maximum. But now we have the interference of two different waves that are being added on top of each other. Now their amplitudes were both 1. Let's look at what happens if we add a wave with a much higher amplitude. Let's say a 1, 1 wave, which you'll remember is diagonal across the box. But this time let's give it an amplitude of 100 and a phase of 0. And now what you see is it completely dominates the picture because there's 100 times as much of this 1-1 wave as either of the other two. And so by eye it looks essentially like a 1-1 wave. There is in fact a little bit of deviation there, but you can hardly see it. And so the amplitude tells you how much of each wave is present in the image. Now let's look at some more complicated waves. Actually, let's get ourselves a clean screen and look at some more complicated waves. Let's add a 2-0 wave with amplitude 1 and phase 0. Now what we have is two oscillations across the box in X. That's what you get with H equals 2. And no oscillations across the box in Y. That's what you get with K equals 0. So it starts at 0 and it rises to a maximum, falls to a minimum, rises to another maximum, falls to a minimum, and rises back to 0. Two wavelengths across the box. Just for completeness, let's look at that from the other dimension. If we had a H equals 0, let's say K equals 3, can you guess what we'll get? Did you guess a wave that had no oscillations in X, but oscillated 3 times across the box in Y, starting at 0, rising to a maximum, minimum, another maximum, a minimum, another maximum, and a minimum, and back to 0. So H and K tell you how many oscillations there are across the box in X and Y. Let's try something even more complicated. What about an H equals 2 and a K equal 5 wave? Again with an amplitude of 1 and a phase of 0. Now what we have is a wave which oscillates, if you look carefully along any X, you'll see that the function rises to one maximum, a minimum, another maximum, and a minimum, and then comes back to 0. Two wavelengths across the box in X. But in Y, in any location, you'll see 5 wavelengths across the box. So we rise to a maximum, another one, third one, fourth one, fifth one, before we cross the box. So this is a 2-5 wave. Now let's look at what a negative K value means. What would a 1 minus 1 wave look like? Well, the answer is, it looks like a 1-1 wave, but instead of having the crests headed towards the upper right corner, now the crests are headed down towards the lower right corner. In other words, a wave, the 1-1 wave headed up and to the right, the 1-1 wave heads down and to the left. But it still has one oscillation across the box in X, and one oscillation across the box in Y. But now, as the X's and Y's are both non-negative, we see the crests of the wave are headed in a different direction. Let's look at something a little bit more complicated. Let's look at a 2 minus 3 wave. Now we have 2 oscillations in X, 3 oscillations across the box in Y, and the crests are headed down towards the lower right corner of the box because we used a negative K value. Now, if we had used a negative value of H instead, for instance, if we used a negative 2, 1, we see we also have a wave whose crests head towards the lower right box. And if we had had both H and K negative, for instance, minus 2, minus 3, amp 1, and 0, now we have a wave that looks very much like the 2-3 wave, the positive 2, positive 3 wave. In fact, there's 2 oscillations across the box in X, 3 oscillations across the box in y, and the crests are headed towards the upper right corner. In other words, this is indistinguishable from the h equals 2, k equals 3 wave. So a -2, -3 wave is indistinguishable from a +2, +3 wave. For the same reason that sine waves, you can't tell whether they're traveling forward or backwards. They look the same in either direction. So when we were looking at one-dimensional Fourier transforms, I showed you on the plots that when the computer responds with what is the Fourier transform of a function, it would show a wave with a positive spatial frequency and also a negative spatial frequency, and that's because the two are indistinguishable. So by convention, we usually only talk about positive h values, but both positive and negative k values, which are all the unique waves that we need to deal with to understand 2D images. Now let's look at what would happen if we start to add together many waves of many different spatial frequencies, amplitudes, and phases. So let's begin with an h equals 2, k equals 5 wave, amplitude 1, and a phase of 90 degrees. So it's a complicated pattern. Now let's add another wave of, say, a 2 minus 3 wave with an amplitude of 3 and a phase of 270 degrees. Now we start to get a more complicated image. And to that, we could add an additional wave. Let's say h equals 8, k equals 3, and to this wave we'll give it a larger amplitude, 6, and a phase of 0. And we have more complexities. Let's add an h equals 10 and k equals -7, also with a significant amplitude and a phase. We get an even more complicated pattern. To this, let's add an h equals 20, k equals -15, again with a comparable amplitude and phase, and we add yet another wave, let's say 3, 3, and 10, and 0. So what you can see is that we can build up a complicated image by adding together many two-dimensional sine waves. And in fact, any image at all can be decomposed into its component sine waves. And this is a two-dimensional Fourier transform, to decompose an image into its component sine waves. And we know which sine waves it contains. They are the sine waves with integral number of wavelengths across the box in x and y. Each sine wave would be characterized by Miller indices, h and k. These are integer values. Each one would have a specific amplitude and a specific phase. And if we added up all those component two-dimensional sine waves, we would recover the original image.